Well, good afternoon, everybody. This is Gene Bohensky with IR Thermal Systems. And in this webinar, we're going to be covering Anderson infrared lamps, applications and case studies. We're also going to be talking about IR lamp technology in general. And hopefully at the end of the presentation, you'll get a good overview of our technology and the way these products work. Maybe give you some help on how to select the right lamp for your application. So let's get started first by talking a little bit about our company. We were founded in 2020 after the former management team purchased the assets and intellectual property of Radiant Energy Systems and Anderson Thermal Devices. The management team and employees have experience in this market since 1985. Anderson Thermal Devices is a New Jersey-based manufacturer of IR lamps, infrared replacement lamps, and shortwave IR emitters and components. With over 75 years of experience in IR heaters and components, we can help you find the right solution for your application. And we offer a broad line of shortwave, medium wave, twin tube, and panel heaters. So we have a wide range of lamps available, as shown on the right. We have short-wave IR emitters, including T3 lamps and T4 lamps, medium-wave lamps, twin-tube IR emitters, infrared panel heaters, custom-shaped lamps, and replacement lamps from most major manufacturers. Here's a couple of pictures of some of our custom lamps, including our Mega Style, Loop Style. So about our company, about Anderson Thermal Devices, we have large volume manufacturing with just-in-time manufacturing, which equates to shorter lead times, lower pricing. We offer standard and custom lamp configurations, and we cross over to common lamps from Ushio, Heraeus, Philips, and other manufacturers. So industries we serve include the converting, paper, film, and foil, printing, non-wovens, plastic, adhesive lamination, batteries, medical devices, filter media, powder coating, PET bottles, fiberglass, advanced composites, industrial fabrics, automotive, packaging, wire and cable, textiles, and many other industries. So how do we determine which IR lamp fits your application? Well, first we start with what material is going through the heater or dryer. We want to understand the ideal temperature that substrate needs to reach, that application temperature, and the dwell time required for that material to stay heated. We also need to understand the absorption coefficient of the substrate, the color, material, and surface properties, and the size of the equipment and area where the lamps will be installed. So lamps are then specified by wattage, voltage, heated length and overall length, connection ends with the lead type and length, whether it's a bare wire, PTFE coated, or other type of lead, whether there's a reflective coating on the lamp, ceramic, gold, or none, whether they are ruby-colored quartz, which is used to cut glare, any other custom construction details that might be required for your application, or just simply a competitor or other vendor part number that you can provide us to do an effective crossover to. So when you take a look at all the different IR lamps available, they're available in different wavelengths, and the heating temperature is dependent on that wavelength. The wavelengths used for industrial infrared heating applications range from 1.17 micron, that's 4,000 degrees Fahrenheit, to 5.4 micron, which is 500 degrees Fahrenheit. There you could see the graph at the right, which shows the three different types of heaters / emitters. Shortwave emitters are 2150 to 4000 degrees Fahrenheit. Those are typically lamps. Medium wave emitters are 900 degrees Fahrenheit to 2150 degrees Fahrenheit. Those can be lamps. We also have long wave emitters, which are 500 degrees and 900 degrees Fahrenheit. We don't really manufacture those, but they are available. So you choose the wavelength based upon the application. So here is a slide with two different materials. On the left is a water film thickness at 10 microns. You could see the absorption factor at 3 microns and 6 microns there. On the right, you have a PVC sheet thickness at 1 millimeter, and there you have a different set of wavelengths at roughly 3.4 micron, and then the others there on the right, where you would want to pick the lamp and the wavelength based upon that application. So here's a couple of pictures. On the left, we have medium wave infrared for powder coating and paint curing. And on the right, shortwave infrared for metal coatings. You can see those bright lamps there. So shortwave lamps are Anderson Thermal Devices shortwave IR emitters that include T3 and T4 lamps. They utilize a low mass tungsten filament to provide a high temperature source that responds rapidly to voltage changes. This allows for precise control during your industrial infrared heating process. They're also hermetically sealed and filled with an inert halogen gas, which helps prolong the life of the filament. And they're available with a white ceramic or gold reflector coating on the back of the lamp to make them unidirectional. So non-glare ruby red Helen coatings and satin-coated quartz lamps are available for filtering out most of the high-intensity visible light. We have shortwave lamp end connections. There's a bunch of those shown there at right. We offer a wide variety of them. Won't go. Oh, no. If you could please mute some of you guys. Okay. So here we have a demo video I'm going to play that demonstrates our shortwave lamps.
Now we're going to demonstrate the shortwave infrared heater. It's in the 1.5 to 3 micron range. It's a quite intense heat in a small package. This particular unit has some air holes for aiding in the heating process, breaking up the vapor barrier. And the lamp itself is made of tungsten inside with a gas that's in a sealed quartz tube. These elements can get up to 3,500 degrees versus 1,800 degrees on the medium wave. So now we'll go ahead and turn it up, and we'll bring it up slowly because it does have a high inrush. So if you're using an SCR like we are, you want to make sure you have a little bit of a delay so that you don't blow fuses. We use high-speed fuses on the SCRs to protect them. So here you can see it's in the just maybe a quarter of the way, halfway, and it will get very intense, the heat. It is okay to look near it, at it, but not directly at it, just like you wouldn't look at the sun. It's not as hazardous as UV lamps are. UV lamps you don't want to look at all. You can look at these. Best not to look at them for an extended amount of time. Shut that off now. As you can see, it's an intense amount of heat in a very small area. Quick heat up and cool down. Thing about these is you can't control them with the thermocouple internal because the lamps are sealed. Best way to do it is with an infrared thermometer measuring the temperature of material being heated.
Okay, that's the end of that demo video. You could see how quickly those lamps heat up. So on to our medium wave lamps. Medium wave quartz tube lamps are available in clear quartz or with a gold and ceramic reflective coating that focus the emitted energy onto the substrate. Those are excellent for surface heating and for drying coatings paint, dyes, lacquers, adhesives, and in the processing of plastic sheet and films. The filament temperature of a medium wave emitter is from 850 degrees to 2150 degrees. Most of the energy generated by the medium wave lamps is in the range of the electromagnetic spectrum between 2 and 4 microns. So at this point in the presentation for the case studies, I'm going to invite Kurt Leach to talk about the 4 case studies that we have. So Kurt, you can start with a corrosive environments case study.
Thank you, Gene. Yes, basically this application involved a heating of a coated web. It was a drying process that, as the web was being heated, it would give off a corrosive vapor that was able to enter the inside of the medium wave lamp, which are non-evacuated, and it would interact with the element itself, causing it to prematurely fail. What we did is we worked with the customer, and we came up with a simple solution. We basically sealed, even though the customer was absolutely convinced, and in fact they did a lot of testing, that he did require about 2.5 microns, and which was about, I don't know, 1750, 1800 degrees Fahrenheit. So we needed to take that same wavelength and coil, and we encapsulated it into a quartz tube, and we were able to seal it, to evacuate it, and have the ends sealed so that it was protected hermetically against any vapors that might be present. The life expectancy of the lamps jumped up. Basically, this premature failure problem was eliminated. The next slide is a very interesting application, which a lot of us really don't realize happens anytime you go to look at a new car. You see the sticker that has the EPA estimated mileage for highway miles and for city miles. And the way that these are determined is a very strict method of basically each manufacturer that sells vehicles in this country is required to run testing where they elevate the temperature of the car, basically to simulate the effects of the car driving in the desert sun with the air conditioning on. And while it's doing that, the dynamometer, the system, is actually being able to monitor and sense the fuel mileage at that very moment. Let's go on to the next slide here. Now, these are very carefully specified specifications by the EPA, and once the vehicle exterior temperature has been brought up to the proper level of temperature according to the spec, the dynamometer then utilizes the proper simulated vehicle speeds. I think it's 35 miles an hour for the city, and I think it's 65 miles an hour for the highway, to derive what those two amounts, the actual mileage, how many gallons, how many miles per gallon they are able to achieve. So anytime you look at a vehicle's EPA estimates, it's not just a guess and by golly. They're not allowed to just say whatever they want. They are based on a very carefully orchestrated system that determines this.
And Kurt, what were they doing before they used our lamps? I know this was something that we made specially for that application, correct?
That's correct. What they used to do is they used chambers that were actually convectively heating the air up, and it could take a very, very long time to get the actual body temperatures up to these levels. And obviously, there also were operators that were in the vehicles when they had to bring the cars in to bring them out. They could leave them in there and leave the vehicle while it's on a dynamometer because the wheels are not, touching the ground. But the fact is that it was a very problematic issue, and it was found that by utilizing, and in this case, we used a shortwave infrared lamp because it had the wide range and the fast response that was desired for this application. The ability to run a test, I don't know the exact cycle time, but I can tell you that it was cut by a factor of about 8 to 10 times shorter to be able to do this with the infrared. So it really was a big success, and it's the standard of the art today by all the manufacturers. And we're very pleased that they're utilizing it, and it still goes on today. This all started back in the early 90s, and it's kind of been proven out very well. Okay. The next application is also in the automotive and in the marine or any other industry that requires complete encapsulation and weather protection of electronic devices. What we're looking at in the photo here is a marine engine controller for an outboard engine. And basically the manufacturer, has the circuit board with all of the ICs and all of the components on it ready to go, put inside of a housing, and then a 2-component resin, polyethylene or polyurethane resin, is then applied into the chamber and covering by about a half an inch, covering the circuit board. The material actually wraps around the bottom of the circuit board to encapsulate it. Before they started to utilize the infrared, this would then go into a convection oven where it could take anywhere from an hour, depending on the mass of the part, anywhere from 45 minutes to an hour thermal cycle. Okay, and the convection oven had to be put at a lower temperature because the components themselves were not able to. Well, in this case, it was 160 degrees. They did not want to thermally stress the components. The answer is that because we have line of sight to the resin, we can actually see it. There's no cover on these assemblies at this point. They do cover them eventually, but they're not covered now. We are able to actually have line of sight, and utilizing a shortwave infrared emitter at about 1.7 or let's say 1.8 microns. If we go back to the earlier part of the presentation, you remember looking at those absorption curves, we find that the polyurethane was very transparent to the infrared at this level. Therefore, the infrared itself, the energy, was able to pass through the polyurethane and be absorbed by the circuit board and the components. It would elevate the components and the circuit board to approximately 130 to 140 degrees Fahrenheit, whereupon this additional heating was able to speed up the resin, the 2-component resin, which is an exothermic-based cure, meaning that the chemistry is such that you have a resin and a catalyst, very similar to fiberglass, where you mix the two and it will harden over time. By utilizing the infrared, we were able to get the thermal cycle down to 1 to 2 minutes, depending on the shape and the volume of the resins and mass. This is very successful. Again, it's pretty much widespread throughout the industry. It's not everywhere. We do still see some really large convection ovens that have to hold thousands of engine controllers in them in order to meet the production cycles. Whereas you can do this inline with an infrared system, and basically as quickly as you can dispense the material, you can actually cure it in the next couple of stages and offload. So the simplicity is monumental by comparison. This next application is quite interesting. This is a pleated filter that requires it to have end caps on both ends of the filter. The position on the far left here shows the actual heating device is retracted down below. It's ready to engage heating the end cap surface and the surface of the pleat also to preheat it. In the past, before they were using any type of thermal welding, they would use, again, a two-component exothermic resin or epoxy to bond these two. And this could take up to 24 hours. It was done in an ambient environment. And basically it's, it could take up to 24 hours. So they would have to, put together a whole bunch of filters and then let them sit before they could pack them out and ship them, test them, pack them out and ship them. With the utilization of the infrared, we were able to take a filter. The polymer end caps were reformulated slightly so that the polymer would allow a softening when it was heated. So we basically engaged the infrared onto both sides of the assembly. We heat it to the point that it becomes softened properly. The infrared device then retracts below, and automatically the end cap was pressed onto the filter, pleated filter assembly, creating that end cap. It's a 100% seal. The two-component resins at times had gaps. It wasn't quite as uniform as they'd like, and this really helped them both in quality, dramatically improved productivity, and resulted in a lower cost of goods, and as I said, improved quality. So that's another very good example where infrared, really can make a big difference.
Thanks, Kurt. Those are great case studies, really showing also our experience, right? And being able to solve customer problems like this.
Thank you.
So just to wrap it up, to go through some general characteristics of infrared heaters. We find that they're easy to zone for uniform heating of the product and width changes. There's fast response to changing process conditions, including quick startup and shutdown in most styles of heaters. Lower initial capital installation cost, including floor space savings. Infinite turndown, and often added to existing conventional dryers to increase line speed and improve process quality. So infrared heater applications include industrial drying for powder coating and paints, coating, annealing, filter media, as we saw, nanofilms, battery, and fuel cell materials. As solvent chemistries become more complex, IR heating becomes required due to faster response time and better control of temperature. And for plastic for embossing, medium wave infrared directly heats and softens the surface quickly. And for water-based coatings on film, medium wave infrared directly heats the surface and is the most efficient wavelength for water evaporation and can be used with or without air. Air removes the steam and prevents skinning effect. Improves efficiency of IR to remove volume solvents. So infrared heating applications are used for adhesives, impregnated fiberglass, food applications, to improve paint quality. New coating methods require constant high heat for proper curing. Metal processing, IR emitters can be precisely adjusted to the product and process. So medium wave IR drives faster on the surface, while short wave IR tends to penetrate deeper. High gloss metals reflect very strongly, while dark surfaces absorb the heat well, and each metal absorbs heat differently. And flat sheets or solid blocks heat up at different rates. So in general, IR improves the energy efficacy of drying applications. So here's a couple pictures, applications in-house of us deploying T3 and twin tube lamps in heater assemblies. Here's combination T3 lamp and hot air system pictures. And last but not least, we have a rental heater program. So heaters are available in widths from 12 to 84 inches and 240 volt, 480 volt, 1 or 3 phase. Rental packages include heater, blower, and control panel, designed for quick trial setup. It's plug and play. We have rental terms as short as 1 week available, and test units are available for running trials in your facility or on your line. And we can do the same thing with lamps if you want to test them in your own application. One of the things that we've learned is that sometimes customers need to get some experience with this technology to understand how it works on their process. And as a company, our team wants to be right behind you to help you do this and realize your own process improvements. So at this point, we welcome you to contact us today with your application. You can email our sales department at sales@andersonthermal.com or call our phone number